Hi, my name is Jeremy Harden, and in today's Node Bible entry, we are going to talk about the path deform node. Let's jump to Houdini to have a look. So I find it useful when talking about the path deform node to understand that there are a few ways of working with curves and how those curves or wires will influence geometry. So what I have here is a quick setup to show what path deform is ideally used for and the kinds of scenarios it is used for, and scenarios that other tools would probably be better suited. So to help understand what it is, let's look at a few examples of what the path deform isn't and why. So first, let's look at the chain SOP, where we have a quick example taking a glyph and using the chain SOP to create a chain around this object. So what I think illustrates it well is if I take part of the curve that is driving the formation of the chain, and I have a point isolated, we can see that the curve is being used to create links in this chain or to create geometry. And so as I modify or extend the curve, we can see links appearing. Another quick example would be the wire deform SOP, where we have an object that's already created. Let's call this a vine. I think we're being generous in calling it a vine, but let's say we have a vine here draped across the table clock. We want to be able to control the vine shape through a wire. So again, I've got a handle that allows me to modify an underlying wire. And this allows us to treat a wire a bit more like or a path, a bit more like a character rig. So for speed, we've just got a wire that we use to create the vine, then just using that same wire to repose it, change something about it. The path deform is best thought of as a guide that a character may walk along a path, an object will travel along a path. So here, to illustrate that, I've got a little toy race car. I've left the path visible and just a little bit of a trail there to show that if we want an object to travel in a specific direction and we want to control that direction with a curve, a path, then the path deform SOP is for us. So let's dive in and have a look at some ways that we can control the path deform SOP. So to understand the path deform in its most basic form, let's start from scratch and create geometry. In this case, I'm just going to use a sphere. I will scale that down. And then a spiral. And a path deform node. So with those connected, our sphere has jumped position. And we'll look at ways that we can control how the sphere aligns to that particular path. For visualization, once again, I am going to merge the path with the resulting deform so that we can see exactly how that path is driving things. Let's view our merge. So in its most basic form, the map length using parameter and offset position using parameter are what 90% of the use cases are going to be. So if I change the offset position using, you can see that it is sliding the sphere along. 0 is the beginning of the curve. 1 is the end of the curve. There are other ways we can drive the object forward. So instead of using a normalized value of the curve, we can use a distance. So in this case, it has gone 1 unit along the curve. So we would need to continue driving it if we wanted it to continue all the way to the end of the curve. If we wanted to let the geometry size decide how far along the curve it is. So if we wanted it to be 10 spheres along, if I plug in the number 10, it has now gone 10 sphere lengths along using the bounding box. The map length using is a little different because it allows us to elongate the object along the path. So instead of using geolength, right now, the bounding box is saying the sphere is this size, and so the sphere is occupying roughly its own size on the curve. If I put this to 2, it's now going to take 2 sphere sizes. So rather than sort of type in numbers, I don't love the handles for this node, but it's very good for getting to grips with ways that we might interact with it as an artist. So I'm just activating the handle option. And we now have some new manipulators, which I will drag for the sake of showing what we can do. So here, this manipulator is changing the map length using. If we instead want to do fraction of curve length, let's go back to a smaller value. So this will use whichever metric is activated here with the map length using parameter. And of course, all of this can be animated in the normal way in Houdini with an Alt left click on the parameter with the keyframe set. So these can be static values or these can be animated values in the normal way. This parameter is sort of making our start point. Now it's saying offset position. That's useful to remember, but for the sake of interacting with the deform node, we can see roughly how it's working. I'm going to jump ahead to a few other parameters that we will be covering in more detail later, but since we have the manipulator active, it's useful to have a look. So I will add a deformation taper because this adds a new handle. I will also add the rotate, and that is rotating the object on its own z-axis within the deformation of the path. And rigidity does not interact with the handles. We'll cover all of these shortly. So the basics of the path deform node, or it takes an object and then wants to help it travel along the path. If we keyframe animate this, let's switch this back to geo length because we want the sphere to take roughly 1 sphere. I'll go off of the universal handle, universal manipulator, and then I'll go back to curve U position and just do a quick animation where we go to frame 1, we Alt, left click the U position, let's go to the end, and change the value, Alt left click, we have some animation. Great. With the preserve volume, this interacts largely with the fact that we may have stretched the object. So right now we're not really stretching the sphere. If I take the 1 and make it a 3, so now we're stretching the sphere, that has now increased the volume inside of the sphere, so it's gained mass, which if we're aiming at something that's realistic, we might not want that. So preserve volume as we make it elongated in one area will then contract the other to keep the volume roughly the same. And similarly with making a shorter length. So This is a high level, create something from scratch. Let's now look at a few other examples that allow us to isolate each individual behavior from each parameter, which I think is pretty fun. So let's look at mappings. So again, we have a car, little boxy car set up with the ability to move it along the path. And mappings is our first set of parameters. So enable deformation is largely turning off and on the node. So I have dived into the path deform network, and it does seem as though there's just a switch at the end that says pass the input. So we've covered a little bit of the options for fractions. So fraction of geolength, using the bounding box, so on. Curve U position. Uniform scale allows us to use the curve to drive the scale of the object that's on it. So that seems a little obvious from this, but we're starting to get into some of the exciting things about this node because it's almost infinitely or limitlessly customizable. It's really, really cool. So if there is an attribute on the curve itself, so in this case, I've got a spiral and I have created an attribute called uniform scale. If there's an attribute, we can have the path deform node read the attribute and set the scale from the curve. So that's not necessarily easier than just using the slider. There are two reasons why we might want to do that. One is tools like the path deform usually sit within a pipeline. There is an element of trying to proceduralize motions. And so we may not be plugging something in and then interacting directly with the path deform node. This may be part of a setup, in which case we want things like the scale to inherit from the curve, which again might be procedurally generated. One thing to point out about that, the scale attribute is a primitive attribute. This curve is one primitive, so it has one value. So it wouldn't be useful to have the scale changing over the length of the path. If we have multiple primitives, and this gets a little interesting, I'll enable a second curve here by not bypassing this merge node. Each curve, each path has its own uniform scale, and so that allows us to, with one path deform node, drive two different objects in two different ways, two different directions, and behaving differently. So this starts to illustrate ways where the proceduralism of the path deform can start to create some interesting ideas. It also introduces the idea that we don't necessarily have to have one object driven by one curve. This is getting exciting. I'll jump now to this next network for what I'm just calling a quick tip. So we've already illustrated that the object can have, the path deform can accept multiple primitives, and it will drive multiple objects along multiple paths, or one object along multiple paths. So we have a boxy plane object and a bit of animation already applied, which is sending our plane along a path. There are two paths, a spiral and a helix, so there are two planes. But if we wanted, we could have multiple planes being driven along with one path deform node. And this is kind of fun. So let's start with, we've got our boxy plane, some incredible modeling there. And then here we have a quick point generation. So we're using a sphere, we're using points from volume, which, if you aren't aware, can accept geometry and then will scatter inside of a geometry shape rather than just on the surface, which is really cool. Creating a p-scale attribute, and then creating a bit of noise that has an animation in the offset. The introduction to Houdini videos are a great resource to getting into expressions, but essentially, rather than being a keyframed value, $F means look at whatever the frame is, and then change the offset over time by rereading that frame value as the slider changes. And then that's a whole lot of change, so then we're dividing that frame value by 192 to slow it down. If I then use that point cloud and use the copy to points SOP, we now have a nice little ambient bit of motion of planes flying in formation. I don't know that it's incredibly safe. I think I've seen some collisions, but we do have some interesting idle motion within. If we now take that, quote, one object, plug it into the first part of the path deform, and then have multiple paths plugged in, we have quickly created a setup that is simple, but breathes a bit of life into a scene. So this has absolutely been used in fish tank or underwater settings where we need a school of fish to travel in a particular pattern, need that pattern to be art directable, and it needs to be alive, or in areas of flight. So this is a really straightforward way of prototyping something before promoting it out to a simulation, or if it's for a quick turnaround project, this can often, with the right lighting, shading, deformation, texturing, this can often get all the way to a final. So it's a really cool, quick way of taking an object or objects and getting them going where we want without having to keyframe a lot of individual positions. Let's go forward now and look at an interesting setup at the top, and that is the piece attribute. So if we're familiar with tools like the copy to point SOP, it's not unusual to be able to take a point cloud and use attributes to put multiple objects onto the point cloud and decide which point gets which object. This is a similar and straightforward workflow where we've got a boxy car and a boxy plane. So those are merged, only this time they have a name attribute. It's a primitive attribute. In this case, the car is named car, plane is named plane. And then the curves also have attributes. So name, car, name, plane. So each different curve has those attributes. If we don't specify, it copies the car and the plane onto both spirals. If we do specify a piece attribute, it allows a matching system between what the object is called to itself and what the curve expects. When I was looking at this node for the node Bible entry, I was reminded of a shot in Sorcerer's Apprentice, Disney Sorcerer's Apprentice, where the evil character has a sort of spectral form, and their spectral form has worms inside of them. So when I saw that Path Deform allows multiple curves to go in, I thought, this could be interesting to try to do just a basic version of that. So what I did is I took some test geometry, in this case that comes with Houdini, Crag, and just did a setup that will populate the interior of that volume with some curves. So we can dive into that another time if there is interest. But this is a basic setup that will take any polygonal object, in this case the pig head that comes with Houdini, and populate it with curves. Of course, once we have a curve shape, we now know enough about the path deform that we can take any object and replicate it along each of those curves. So if I now view the path deform, we've got a basic wormy setup that can move, have the worms kind of crawling within the geometry volume. So if we wanted to make this more complex, we might have the outer geometry visible and then use some kind of noise to reveal kind of in a damage way, and then we have the worms crawling around. It's a fun start to getting a bit of life inside of something at the smaller scale. The shot in Sorcerer's Apprentice was a little bit more complex than this. One thing I'll also note briefly is each of these items coming in is a polygonal object that is being duplicated onto every curve. So if I middle mouse on my curve geometry here, I have 2,993 primitives. We can expect, if we have 75 primitives, that 2,993 times 75 to equal a lot of primitives. So we just need to be aware with system load when we do that. There is the option to pack the object coming in, which again should probably be covered in some of the intro to Houdini courses. But when we pack the object, we lose its bending deformation. So if I bypass that, we can see that it's now, the objects are now curving. So it's something to bear in mind if we are taking this to extremes with lots of curves and lots of polygons coming in. This is also a good way of showing the start and end behavior. When an object reaches the end of the curve, what do we want it to do? So by default, extend is almost always the desired behavior, but perhaps we want each end of a curve to be a hard stop. We might use clip. As the geometry approaches the end of its own curve, it starts to get cut off. And we can see that here. Similar for start behavior. And then if we wanted to clamp, that essentially begins to flatten the object at the end. So clip, in theory, is reducing the primitive count of the driven object. Clamp is just compressing it. Most use cases will just benefit from extend. The obvious caveat, though, if we extend a lot beyond our original curves, we get a little bit of a worm explosion, which could be a desired effect, but might not be. So this was just adding a basic subsurface, maybe spooky lighting, a bit of moody rim light and underlight to give it a bit of shape. But again, if this were taken to a shot extreme, there would probably be more layers to the effect, maybe a skeleton inside to see through the subsurface, and then possibly some of the outer geometry visible and masked. But that's sort of playing with renders when we should be looking at the path deform stop. So let's jump back to that. We've largely covered the mapping section. I will, just for the sake of completeness, point out that just like the uniform scale can be driven with an attribute, the map length using value can also be read from the curve. And this is where the path deform is great as a node that sits inside of a larger setup doing tens or hundreds of shots on a project, just running through procedurally and doing some really cool things, because the curve, all of these parameters can be set by reading information from the curve in the same way as uniform scale. Again, these are attributes that are on the curve not attributes that are on the driven object. So let's move to the deformations section. So there are three types of deformations in the path deform node. The first two behave fairly intuitively, and so I'll start with those, and then rigidity is its own animal. So I'm going to look at taper and rotate first. If I introduce taper, I add the ability we saw with the handle. Let's go ahead and do that. Let's re-enable our manipulator. Look at our taper. So that's changing the base scale factor. Taper is best thought of, though, as a whole curve parameter to change the size. So this is just changing the internal scale of our object over the whole length of the curve. So no matter where I place the position, the taper stays the same. But if let's set this back to 1, and if we do the scale ramp, this ramp becomes a representation of this is the beginning of the curve, this is the end of the curve. Now, as we bring the plane further into the curve, we can see that it is starting at a very scaled down position, reaching normal scale, and then scaling back down. So if we go sort of halfway, we can now control the size using the taper. So I'm not sure of a creative scenario where we want an object to change its width or its stretch over the course of a curve, but that's the power of this tool, that it's built for scenarios that I can imagine and those that I cannot. So this covers taper, and again, there is the ability to have an attribute on the curve that drives the taper for full proceduralism, so it can vary over the course of the curve. So I'll also point out that the uniform scale is a primitive attribute, but as we get into deformations, they become point attributes, and so they can change. So uniform scale will be one scale over the whole primitive, the whole curve, the whole path, whereas the taper attribute, or the rest of the deformation-based scale by attribute, can vary over the curve because they are point level attributes, not primitive level. So if we enable rotate, let's do scaling. We have a global value here to change the rotation as we go. We could animate this. That's absolutely fine to work artistically and animate. Use this to have the plane banking as it flies. But I thought it would be useful to demonstrate the scale by attribute using the rotate attribute. So if we use scale by attribute and we specify, we have here a noise which is applying a different rotation throughout the length of the path. So as I now move the plane along, we can see there's a varied rotation. It's kind of wobbling along because it's reading the rotate attribute from the curve points. We can actually see those if we jump to the geometry spreadsheet. There is a rotate attribute. And for the sake of this noise, I have the attribute being -1 to +1 so that it is able to bank left and bank right. So if we jump back to the scene view, the base rotation, 45 degrees, can be multiplied by 1. It can bank 45 degrees, or it can be multiplied by -1, or anything in between, so that as we traverse the curve, we are getting random rotation. maybe we want more extreme. So we can randomly go up to 90 degrees. Or maybe we want less. 10 degrees. Just a slight bit of variance. Feels almost like a paper airplane with the minor variant. So this could be good for that. We needed a paper airplane to travel through the scene. So if we don't use attribute, we can do the exact same thing that we did with taper and instead use a ramp to control the rotation over the course of the curve, where this is the beginning of the curve and this is the end. Let's say 360 is the end. This is now at the beginning of the curve. I would expect 0 rotation. And over the course of the curve, because of the ramp, I would expect it to be doing the entire 360 degrees. If we go halfway and I wanted to introduce a bit of change, I could click and drag and control this way. For me, taper would be more intuitively controlled with a ramp. This is a personal preference. And rotation, because it's not clear exactly where we are in the curve in terms of halfway, I would more likely use an attribute. So by default, rigidity is off. Our plane, as it extends along the curve, just being cartoony and warping along the curve. If we, in the case of an aeroplane, wanted to have the direction, the aim of the aeroplane and the position of the aeroplane be driven by the curve, but not warp it, all we want to do is toggle on rigidity, and now it's a rigid object. The reason it's a rigid object by default is because the rigged group is everything. So nothing is everything, so everything is rigid. Fine, make everything rigid. If we wanted something a little more complex than that, we should go to a different example. I have created a really weird set of 2 boxes with some stuff in between joining those boxes up. So rigidity is on, it's kind of a dumbbell shape, and we're moving along the curve. So now it's just keeping its shape completely, and if I turn rigidity off, it is bending to follow the curve as well as aiming. That's fine. But if I wanted to say that the ends were made of stronger stuff and rigid, and the middle is more flexible, I can actually use groupings on the object. So this is where we start to get into things on the object, the driven object influencing its deformation rather than attributes on the curve. So if I say by rigid group and then choose the rigid group, we are now looking at the fact that these polygons, these primitives are grouped to be part of the rigid group, and these are not. And what that means is as I change aspects of the map length using, it's difficult to say, the part that deforms is the part that is not in the rigid group. So, and I can take that to extremes, and so on. And that will continue as the object moves around. Rigid group is probably the most useful of ways of defining rigid things. Rigid group is very powerful, and it also gives us the ability to do stretch softening. So if I take this, let's say 2, there is a boundary where we have things that are in the group or not in the group, and stretch softening allows us to change the fall off for that boundary. We've got a couple of different ways of measuring that, edge and surface. In this particular object's case, since the edge length and the surface are fairly tied together, we're not getting a lot of difference. We could, for example, find that to be a little bit too drastic, and so maybe we want to even it out a little bit with a soften radius creatively. Additionally, that soften radius, we can further control the fall off of that radius with a ramp. So in this case, we are changing positions along the ramp, which we could do creatively, left and right, up and down, to achieve exactly the art-directed fall-off that we want. Within softening the stretching. If we turn that off, all of that goes away. We're not using it anymore. Let's talk about the allow rigid geometry to stretch. So I was a bit confused by this parameter because, to my mind, the idea of rigidity meant I did not want it to stretch. So as I'm saying 1 or 2, I want the rigid things to not stretch. Again, this is not something that I see a use case for, but I'm sure that there is a procedural setup that will benefit from this. Allow rigid geometry to stretch takes the rigid geometry and in the forward direction only allows the object to stretch. So instead of having nothing rigid, so let's turn off rigidity, we're getting skewing in things that are meant to be rigid. So our end cubes there are becoming not cubes. So if this is meant to represent a shape that is metal and then accordion, let's say a bus with an accordion section in between, this no longer looks like a bus. So if we wanted it to keep its form, but stretch along the curves while staying rigid, this toggle allows us to do that. I'm not sure exactly the use case, but it's useful to be able to do. The rigidity mask behaves similarly to the rigid group. Let's look at what that entails. So if we have nothing in the rigid group, everything is rigid. So this is now just a rigid object. What I've done is to illustrate the differences, I've also added an attribute where we say that the interior is not rigid at all, the end cubes are rigid, and I've done that as a geometry attribute, a point attribute that is a float value. So when we change this to scale by attribute and specify the attribute, we now have the ability to per point specify rigidity. And then this is a multiplier on top of that. The caveat I'll give on the rigid mask is if we're lazy or we're less than accurate on our masking, we don't necessarily benefit from stretch softening. We have no local refining of this mask. So this mask may be used in addition to something else, or we may use the mask entirely, but if we're using the mask entirely, the attributes need to tell a story, and in this case, my rigid mask was too basic, where the points are not rigid at all, very rigid, and not enough of a fade between them. So I think we can see that the most straightforward to set up in a timely way is probably grouping, where we specify if we want variable rigidity, we use the grouping. And here we can see that it is trying to apply the rigidity mask as well with the rigid grouping. For me, I would say one or the other. I'll quickly also spin through the other ways of defining rigidity, because we've done all of this rigid group where we have nothing, where it makes everything rigid, or we just leave no rigidity. So no rigidity, some rigidity by group, or everything is rigid. So if we set by geometry fraction attribute, we could have points that say a curve position, where they should be on the curve. So instead of the attributes on the curve driving a piece of an item, we might have attributes per point saying where they should be on the curve. And then by piece attribute gets into the idea of using something like a connectivity SOP to have multiple pieces. So to best illustrate the last portion of rigidity, I have a slightly absurd example, which is a pig with a helmet. So when I first saw rigidity as an option on the path to form, I immediately thought of a character with armor where we have got fleshy bits of a character and then rigid bits. Okay, so if we now have by rigid group as before, and this is perfectly illustrating some of the complexities of rigidity. This helmet is made of multiple objects. So there are two different objects internally to that helmet. So rigidity is saying make every piece rigid. And so we now have the pig, one piece of the helmet, and another piece of the helmet all being made rigid differently. And that is an ideal, as we can see, for the path to form node to have decided how we want to handle individual pieces. So we can again use rigid group, where I've said that the helmet is rigid, but the pig is not. If we do rigid group, the path to form node decides how it is going to handle multiple shapes. But by doing piece attribute and then using our mask, we are saying, because this is a painted mask, the face and the helmet are painted to be completely rigid. We now don't have the path to form node deciding how to split out or deal with multiple pieces. Okay, so with a connectivity SOP, we are looking at the individual objects and saying that we are controlling what we are calling a piece. And then, because we have that control, we're not getting necessarily the offset piece of the helmet traveling away from the main body of the helmet, because internally path to form was deciding what a piece is, and now we're deciding using a connectivity SOP. So we are controlling that, and that is preferable. So we've covered at great length the rigidity parameter of the path to form SOP. This is all on the first tab. But thankfully, the second tab is more of a setup, and most of the default options will work out of the box. We'll just cover them for the sake of completeness. So if I have an object, my sort of stretchy object here, I do want to be able to decide what direction we travel down the curve. So if we jump to the capture and align section, this is really the setup for how an object is going to travel along a curve. So the first thing we need to know is the forward direction. I modeled, vehicles tend to be modeled along the Z axis in Maya and Houdini. That allows for consistent rigging. So the forward direction in Z as a default is a great default. If I had modeled this or imported this from something else, I could specify a different direction. So here now, we're moving along in a different alignment. So this is just the initial alignment. It's called forward direction, but which way are we pointing our object that is moving along the curve? And then because our curve can, here I've illustrated this with our bendy curve, our curve can exist in more than 2 dimensions. There may be an up, down, left, right, not just left and right. We also need to know what direction is up on our object. In this case, my stretchy, weird object is Y up. So that's the geometry that's going into the first input of the path deform, the geometry to deform. Then with our curve control, we have a few different options, and really the use case will dictate what is preferred. I'll just quickly flip through them for the sake of it. So if we have the y-axis up, the curve's y-axis, then we are still having our object follow along, but we lose some of the banking feeling that we might get with the fact that as the curve undulates, we do want a dynamic sort of twist motion to our object. So if we are familiar with copy to points or other tools that we have attributes on the point, so for example, orient, to be able to control the rotation, we do have the ability here to also have an object pull its rotations from attributes on the curve. So if we want our curve to not have a different, so in this case, the curve normal, the up vector is changing as our object traverses along it. If we just wanted a static up vector, then we could toggle this and it would not vary over the length of the curve. Okay, so once we toggle the make curve up vector constant, we then get another option, which is force orthogonal tangent. And that essentially allows us to say that the front of our object as it's traveling along is still changing to orient along the curve, even though the up vector is constant, but it is using the tangent to do so. And as we can see, that unhelpfully brings the back of the object to some odd positions. Focus on the front. So for me, having these be constant and the compute, the force orthogonal tangent are not valuable options. Copy up control to end is taking the up value at the beginning of the curve and making sure the end is the same. So if there were a loop, a perfect circle that this object were traveling along, we wouldn't want the object traveling along. Think of a train going around a track. We don't want the orientation of the train at the end of the loop to be different. So this allows us to, if we had a closed loop, have the beginning and the end have the same up value, even if they are calculated in some way. For this, because it's an open loop, or it's an open curve, this value is not necessarily something we need. So Before I hit this button, I'll save, and I will talk about the fact that we've got a custom option here, here, and here. So we talked earlier about, in mapping, the fraction of geo length. So that is not measuring the object point by point, that is looking at the bounding box of that object, and that is driven by this, the geo capture origin and other settings. So if I click this, it is going to switch this and these to custom, and I will do that. There are cases where we might want to, again, procedurally decide things, but I find the node, path deform node, to be much more out of the box working by not doing what I'm about to do. So if I hit initialize geometry alignment from curve, we get something a little weird. This has tried to look at the front of the curve and our object and to deduce things about which way is forward, which way is up on our object, and where it should center the box of it capturing the object. I would say that's been less than successful. There may be cases where that will be more successful, but if we do want to manually specify the capture origin, I'll slide through some values so we can see it is changing how we capture. But it's good to have control. It's also good for things to work out of the box. So I will switch this back to relative to bounding box. We're still getting some odd behavior, and that's because our forward direction is custom and our up axis is custom. So now we are back to largely working out of the box. Center geometry on curve can be useful to enable or disable depending on whether we want a transform to affect. So for example, if we wanted this to sit on the curve, we may have transformed the object and we might want to keep that. So we might not want to center it on the curve. In this case, I do want to center it along the curve. Now we look at the bounding box and the fraction of the bounding box that we are using. So right now we are going from one end of the bounding box to the other, and we are capturing the entire object to use on the curve. If we wanted to use half of the bounding box, then we might specify where we're starting from, or less than the entire bounding box. So again, I'm sure there are cases where we would like to control this procedurally. I'm just not sure exactly what the use case is. And of course, override allows us to have attributes on the curve. Yes, an attribute on the curve to specify how geometry is captured. And then if we have limited how the geometry is captured for whatever reason, we may have driven it by bounding box, but then something changed about the geometry, and for some reason that was retained. The after end essentially says, even though the bounding box ends there, please keep capturing the rest of the object, and similarly before the start. So then these are acting as a weird offset, but the object is still moving along the curve. And then compute end relative to start, in theory, means that the end, if I were to do this to 1, that the end should be 2, because it's just adding together. The geocapture end is now meant to be the end plus the start. I haven't seen that working. I'm not sure if that is something that needs to be looked at, but this particular toggle has not behaved the way it is documented. So I'm not sure what the use case is for that, but I haven't seen it functioning the way it is documented. Uncaptured geostretch is something that I see as a troubleshooting tool to see what has been captured by this step. So for example, if I specify a reduced section of the bounding box to capture, I then can stretch things that are uncaptured and so quickly see what am I not capturing. So if it wasn't clear from this, what am I not capturing? This is also overridable. So again, there may be a procedural setup where someone is wanting to do something creatively with the uncaptured geometry. But for my use cases, this is largely a diagnostic tool to make sure that I've got everything. Because if I do have everything, this does nothing. I'll quickly say this is kind of a convenience feature. So very often if we're using a curve to drive the motion of things, we may realize that we've defined the start and the end the wrong way, and then we need to drop down a reverse, something to reverse the curve. In this case, it's built right in. We can say, oops, I did the curve the wrong way. Please reverse the curve. And then if we do, we may also want to reverse the normal, but we may not. So we have the option, if we have done something reversing, that we can also reverse the normal. So blend tangent is quite useful in a certain set of cases, and I'll do my best to explain that now. So if we have quite a noisy curve, everything about the object being driven along is absolutely driven by that point that object is nearest. So as I move this object along, if this is a very noisy curve, we can get a behavior at each part of the object that is also very noisy. So it may be that we want the motion of the object to not necessarily just look at the point that it's on, but perhaps a larger area. So if we set our blend strength, we can then say the number of iterations that we want to look at. And so we can see, as we look at the end here, the more areas of the curve that we look at by increasing the blend iterations, the more that our position is adjusted. And this can give us a smoother performance going along the curve by looking at a few different points rather than one. So this can be very useful. If we're looking at an object moving along the curve, that might not be very noticeable. It's a subtle change. But if we have used our object to also drive perhaps a camera motion, that can make a bit of a difference. So if we look at the attribute section, we can see by the fact that the text is not bold, that this is not modified from the default values. It's rare we would need to change the default values, but I'll quickly run through them anyway. So attributes to transform. Essentially, when we deform our objects along the curve, we are looking at if we're looking behind the scenes, we're looking at the P attribute, the point attribute of the mesh. When this says attributes to transform, that is saying that as we deform the object, please transform the points. Now, misleadingly, I looked at this and I thought that if I had a rest position or a reference position for textures or fur, that would also be transformed. And oddly, it wasn't. So it seems as though there's an internal logic where it's deciding what is relevant to transform. Essentially, in practice, I've seen the wildcard asterisk there to mean P and N. So no visual change. If I've added other attributes like a rest position, it has not translated it. So I'm not sure what the logic is there, but star for the effect of This parameter seems to effectively mean p and n, and if we don't transform the normal, we get odd things. We can then recompute affected normals, and if we're doing a lot of, and we can see that that's visibly there, if we're doing a lot of deformation, we probably do want to modify the normals based on the new deformation rather than just read the normals from the geometry itself, in which case we would want to recompute. And then preserve normal length. We just want to make sure that as we stretch and bend things, that the intensity of the normal stays the same intensity. So the direction may modify, but we don't want it to become a more intense normal. That's probably a more advanced topic for another day in terms of shading, but preserve normal length is a good thing when changing normals. The last two parameters here, I think, are very, very interesting from a pipeline perspective, because we have two objects, and internally, I haven't specified the name of each object. So we've got one object going on to two splines. So once we've created our performance, the information on how the performance was created in terms of which spline went onto these objects and where on the objects these are, that information is effectively lost. These allow us to keep those attributes on the resulting geometry, which is really cool from a pipeline perspective. So if I go to the path deform itself, let's see, straight to the path deform, and look at the geometry spreadsheet, the curve position of each point is preserved, and the curve number, which curve that object was applied to, is also preserved. So in theory, we could, if we needed to reverse part of this process or troubleshoot, we could look at why did that object end up at that point in space? It's because of it was on curve number 1, and it was at that particular curve position. So if we get unexpected behavior, we've kept a way to troubleshoot and peer into how exactly that performance was generated. We did cover the piece attribute group and curves associate with the geometry coming in and the curves, so we could isolate by group, and then we could specify what the group type is. So these are typical parameters on almost every Houdini node of this type. I thought it could be fun to just throw together a bit of fun. So what I did is I took a helix, normal helix, ran it through a similar process to what we've done before, so a mountain to give it a little bit of a vertical variation, and then I used the chain sop to repeat a box along the length of that curve. I then used two grids and a sweep sop to create some rails. You can probably see where I'm going with this. Then doing a little bit of a boxcar feeling, some beautiful modeling there, and the path deform. I thought it was fun to take one curve, one path, and using a few different tools in tandem, create sort of a toy roller coaster, minecart, boxcar setup. So this isn't one of the examples that we covered earlier, but I thought it seems a bit of a waste to have gone through the settings of a curve and not use it. I thought it might also be interesting to take that motion of the cart, create a group, which I'm calling rivet, and that's just all the points on the cart, and then riveting a camera to the motion of the cart. So we can now look through the camera, and in a matter of 5 minutes, we've got a basic toy-like motion, which is moving through the world with a bit of fun. Hopefully this has been a useful exploration of the Path Deform node. You can find more Node Bible entries and quick tips just like this by visiting cgforge.com. Thanks very much.